Now I will talk about the Coriolis effect, which is one of the most fundamental mechanisms in the science of meteorology and oceanography, telling us how the rotation of the Earth affects the motion of air and water parcels. And again, the problem is not in the mathematics, it's quite simple, is to understand what the mathematics tells us and link that to what we observed in the ocean and the atmosphere. And it's not a long lecture, so if you have any questions, I'm happy to refer you to an article I had recently published in the Royal Meteorological Society's journal, Quarterly Journal. And it gives more details about what I am about to tell you. So here is the reference. Now, the article in Quarterly Journal said that the Coriolis effect is not an optical illusion, which actually you can find in some textbooks, both said implicitly and explicitly that it's really not something real, it's an optical illusion. And this is because it's also said, and it's quite true, that the Coriolis force does no work, and it's a fictitious force. And this is true in a scientific language, but it might be misleading to take it as we normally talk about not doing work or being fictitious in a colloquial way, everyday way, which actually implies that it is of no substance. The Coriolis force is actually quite powerful. And to show that, I will show you two short passages in a famous movie by Stanley Kubrick from 1968, I think. It's called 2001, A Space Odyssey. And here you will find something that you might have already become familiar with in science fiction movies, the rotating space station. It was an idea in the 1950s, and the idea is that a rotating space station will generate artificial gravity because of the centrifugal effect, so it would be quite normal to work and live on the space station. And one episode in the movie is the very start of the film, and perhaps I should, yeah.
Which is after that we...
So let's... I can take it. So one very important lesson we can draw from the beginning of the film, and I will show that now. So this showed the gigantic wheel spinning slowly and the approaching rocket or rotating in the same degree to be able to come in. And the second passage is from inside, and it shows that you can live a normal life because it will feel the same as on Earth with gravity. And this short sequence showed that you can even make gymnastics and jogging on this space station. So here he is weightless because that is in the center of the rotation. But else he has a weight. They can walk normally. Now, this was how do I go back to? So, this was the way the scientists, the technology have thought to solve the problem with weightlessness. For example, in this case it was a rocket obviously heading out in the solar system, a very long journey, and for that purpose they had to have artificial gravity. And about the same time as the movie was made, scientists in both Soviet Union and the United States discovered that this would not work. And the reason was the Coriolis force. The Coriolis effect would make this impossible. And that should actually have been realized before they started this, because it's all contained in the work by Gaspard Gustave Coriolis, who lived from 1794 to 1843. And his paper actually tells why this would not work. Because when the space station or the space rocket is rotating, everything is fine as long as you stand still. But when you start to move, you will be affected by the Coriolis effect. and become dizzy, perhaps not be able to walk properly. Washing machines, gramophone record players, and all moving objects, human and machines in this space station will be affected by the Coriolis effect and at worst malfunction. The interesting thing with Coriolis is that his paper from 1835 does not deal with the atmosphere or the ocean, but actually with machines, very much like the space rockets. Now, why does this happen? To make it very simple, here we have a simple centrifuge. It's a machine where something is rotating. It's this blob here, and then, as you all know, we have a centrifugal force pointing out, trying to throw it away. And this is what we normally feel when we are on a carousel or in a bus that takes a turn. Now, what Coriolis was active in the time of the Industrial Revolution, when they developed new machines, often in competition with, for example, British or German manufacturers. So the French wanted to make their machines as good as possible. And the question was now, if now this object is moving relative to the rotation, inside the rotation, how will that affect the centrifugal force? Do we have to make changes in the construction of the machines? And so here we have simplified, seen from outside, something that is moving from outside to inside, while at the same time taking part in the rotation. And then the trajectory is no longer along the circle, it's crossing the circle, but the total centrifugal force on this object is still pointing perpendicular and now slightly off the radius as it was before. Still, there is a common centrifugal force pointing out from the rotation center, and the difference between these two forces is what the Coriolis paper deals with. The force we have to add, so that this Coriolis force, which of course he didn't name, it was named long after his death. This Coriolis force we have to add to the common centrifugal force to get this force that interested Coriolis and the French technologists in the 1830s, the total centrifugal force on this moving object. And he was not interested in his force, he was interested in this combination of the forces. But we are interested in this little force by itself. And now to have some mathematics, just to show that it's not just nice talk from my side, it also has a basic in mathematics. Here we have the standard equation, which you can find in all the textbooks, of the relation between relative acceleration, absolute acceleration, the Coriolis force per mass unit, and the centrifugal acceleration. This is standard textbooks notation. And we can apply that on the carousel, the flat carousel. So we have gravity pointing straight down, the centrifugal force pointing outwards, and their sum is also pointing outwards, downwards, but also slightly out, so it does not prevent the object from sliding out, as we saw in the previous examples. So that is the carousel, where two forces, at least, or three forces, gravity, centrifugal force, and the Coriolis force are active. Now, if we now want to isolate or bring out the Coriolis force in isolation, one very clever trick is to make the platform, the carousel, parabolic. And doing so, we will still have the three forces, but they will in some mysterious way disappear. And so we actually now have still the gravity and the centrifugal force, but together they will form a new force, G prime, which is perpendicular to the surface. And being perpendicular means that there will be no side acceleration. The object will stay where it has been placed. so it will not slide, it will stay where we place it on the rotating parabola. And here is one example of the parabola when the object is just put there. But now if we slightly perturb the object, or if it's colliding with a bumblebee, so it's moving slightly, then from outside it will go over in some sort of ellipse, sometimes higher, sometimes lower. But if we place ourselves inside this parabola, it will look quite different. It will look like a little going around in a small circle. And there's a movie I found on a Dutch website showing this. So here we have to the left the perturbed motion. Something has disturbed the object and it's going around in an ellipse. But seen from inside, it's still going around in the ellipse, but now from inside, it's not going around in a small area. So we can isolate the Coriolis force on a carousel by making it parabolic. And actually a similar trick, so to say, has been offered by nature on the Earth. So when it comes to the Earth, where, as we know, when we deal with the atmosphere, we don't have to think about the centrifugal effect of the Earth's rotation, which is actually quite strong. It has mysteriously disappeared. We only are concerned with the Coriolis force. That is because the shape of the Earth, which is of course a function or a result of the rotation, has made this possible. And I will go into some detail to explain why. But there is again a semantic problem. In the English-speaking world, there is not made a clear distinction between gravitation and gravity. And I think it's also the case in the French, gravité and gravitation. They seem to be used simultaneously or mixed up. And that is not only a semantic problem, it's a scientific problem, because they are quite different. Gravitation is actually the attraction between bodies, between the moon and the Earth, and between individual objects also here. There's a gravitation between these two. But gravity is the Earth gravitation plus the effect of the Earth rotation. And that is what we feel. And these two, as you can see here and we see on other pictures, point straight down. And that's why we don't feel any side acceleration. And the reason is, of course, that the Earth rotation has made it slightly flattened at the poles and slightly expanded in the lower latitudes. And if we go back to the mathematics from this first equation and fill them with some constants, then dv dt is now gravitation, it's an attraction of the Earth, and the centrifugal force we can now specify with R, capital R, as a distance from the Earth rotational axis. And then, relying on the previous pictures, we can combine the centrifugal force and gravitation into gravity, G without star. But now it's very important, just because we do this, it doesn't mean that they have disappeared. They have disappeared mathematically and been represented by a new variable. But of course they are still there physically. And so here we have an expansion of the previous picture. The gravitation that is actually pointing slightly towards the pole, and the centrifugal force that is pointing straight away from the rotational axis. And here is a vertical, and here is a horizontal planes. And of course, gravitation is now, so gravity is pointing straight down along the vertical. So we don't feel any side acceleration as long as we stand still. So now, if we now move eastward, a westerly wind, or we move eastward, and I symbolize that with this agreed symbol for going into the picture. Then of course, by adding to the Earth will rotate from west to east, and we move from west to east, and that means that the centrifugal effect on us is slightly higher than it is if we stood still. So now the centrifugal, outward going centrifugal force is slightly stronger. And it means also that the gravity actually is also, the modified gravity is actually not straight down. It has an angle less than 90 degrees with the horizontal plane. And the difference is mathematically, the side acceleration is 2 omega v, which we recognize as a Coriolis term. So the modified d is now not straight down. And if we go now into more detail in this increased centrifugal force, the increase, how does that look? We have first the Coriolis effect along the horizontal plane that deflects us and the air and the water to the right on the northern hemisphere. But we also have a vertical component which is less known. It's a sibling to the Coriolis effect, and it's called the Eötvös effect, after a Hungarian scientist who were busy measuring the gravitational field of the Earth, and he had to take this into account, that if you move, you will actually, in this case, moving eastward, become slightly lighter, because you are lifted slightly from the Earth's surface by the increased centrifugal force. And this can actually be measured. Here is a record from a French research vessel in the Indian Ocean. And it will also be, so here is, it's first moving from north, moving south, and slightly westward. Then it's moving straight westward. Then it's moving northward and slightly eastward. And how is now this reflected in the weight of the ship? Because that could be measured. So, as you can see, when it moves straight west, it becomes clearly more heavy than
Я потом отключу, я не буду, я потом вырежу.
So how is now this reflected in the weight of the ship, which can be measured? And as you can see, during the short period, the ship is moving westward. It is significantly, at least in these measurements, heavier than before and after. And it should be also kept in mind that the Eötvös effect only is active for east or west motion. It does not change if you move north or south. So now we come to what the textbooks, also Jim Holtner's textbooks, are very vague about. And that is when the motion is from east to west against the Earth's rotation. That is, I think, very important discussion. So here we have now air coming out from the picture. And of course that will weaken the centrifugal force. And the amount it weakens with is the 2 omega v term. So far it's mathematically all right. But when we think about it physically, then something new comes to our understanding. So now the modified gravity is pointing slightly in the other direction, pushing things towards the Earth axis instead of away from the Earth axis as before. And although now the centrifugal force is weakened, it's still pointing out. So the question is now, what is actually physically pushing, accelerating the object inwards towards the Earth axis, in spite of the very strong, still strong centrifugal force? And So here we have now the weakened, the Coriolis effect, which physically means that first of all, the Earth-verse effect now means that an object is heavier, it's accelerated stronger towards the Earth's center. But the Coriolis effect is because, as you can see at the bottom, it's the gravitational sorry. I'll take that from. So here we have now the gravitational. When we look at it physically, we can see that the force as it actually driving the motion inwards is the gravitational attraction. When the air was moving in the other direction, it was an increased centrifugal force that was driving it outwards. But the decreased centrifugal force is still pointing outwards. So the only force that can move the object inwards is the gravitational attraction of the Earth. So here we have again the Coriolis effect pointing to the left of to the right of the motion, and the Earth-verse effect increasing the weight. And as I said, now it's physically the gravitational attraction that is moving the object towards the Earth axis. So, and this is an important distinction. When we mathematically deal with a motion, we can kinematically represent them by this well-known expression that it's the Coriolis effect that is deflecting. But when we want to understand dynamically, physically, we must realize, as I said before, that even if some terms have disappeared mathematically, they are physically still there, and they must be taken into account when we want to understand the physics behind the deflection. And one of them is a real force. And this is actually contrary to what we normally read in the books, that the Coriolis force is fictitious. It is fictitious in a kinematic sense, but not in a dynamic sense. Now, if now a real force is active, that should be seen as a change in the absolute velocity. So what do we know about the absolute velocity in this case? And here is an example. It's a 10 meter per second motion at the mid-latitudes. And it's easy, if it starts at 42 degrees north, we can easily calculate the radius of this so-called inertia circle. We can see between what latitudes it will stay. We can easily calculate the speed of these latitudes. And now, inside the Earth system, there is no change of the velocity. But now we go outside in an absolute frame of reference and look from it outside. And then the velocity is not constant. It's varying. And strangely, perhaps enough, the velocity of in this case, the velocity in the northernmost point, 345 meters per second, agrees with the latitude 42.1. And inversely, the slowest part, 335 meters per second, it's here, agrees with the slower moving 43.9 degree. Now, is this a coincidence? What I show in my paper in Quarter Journal is that it's not a coincidence. It can be mathematically shown that it's a general rule. So here we have this relative motion, the inertia circle, and here is the absolute trajectory, and its velocity at its slowest part agrees exactly with the latitude of its northern latitude and vice versa. So it's, apart from a nice mathematical relation, it also shows that, or confirms that a real force is involved in the deflection, because if not, the absolute velocity would not have changed. And interesting enough, if you remember the popular but in my view misleading explanation of the trade winds or the Coriolis effect, where the absolute velocity was supposed to be constant, leading to a change in the relative velocity. Actually, in reality, the opposite is the truth. The relative velocity stays constant, but the absolute velocity varies. Now, this was a discussion of east-west motion. It can also be done in north-south, but there is no time to do that. But in my paper in Quartal Journal, in the appendix, I have done this with the same philosophy in terms of centrifugal force changes for motion inwards and outwards, northward and southward in a rotating system. Thank you.